Hey, I'm Adam, and I'm gonna share with you some things about sorting, how sorting works in Python, what that code looks like when you kind of get down in the details. It all started when I was investigating a kind of a strange issue to do with performance and algorithmic complexity, and it kind of took me on a bit of an adventure. So I was sitting at my standing desk looking for a solution to my problem. And my problem is this: merging sorted lists. It's a pretty old school, like stereotypical interview question to merge sorted lists, but I actually was encountering it in real life. So here's the way you can think about merging sorted lists. Like I have these two lists, 2, 3, 4, 5, and 1, 4, 10, and they're already in sorted order, and I want to make a new list that combines them and still is in sorted order. So the naive solution is to just take those lists, throw them in a new list, and resort the list, right? But the thing is that resorting a list, even with a great sort algorithm, is n log n time, I believe, in the worst case. So there's a better way to do it. You don't have to throw away the fact that this data has been sorted. So here's how you do it, right? I start with the front of the list, and I look at the first two elements of my two lists. I take the smallest one, I put it in my new sorted list, and then I kind of cross that one out. I move on to the next element of the list. And then I compare those two elements. So then I'm comparing 4 instead of 1, right? And I can see that 2 is the smaller one, so then I bring 2 down. And then you just keep the process going, right? So then I slowly cross off each element, and I build up this list. My head's in the way, but I build up this list here, 2, 3, 4, 4, 5, 10, right? And so that is a faster way to approach the problem because it's linear. I only have to do a comparison per element. Every time I do a comparison, I'm adding a new element to my final list. So it's linear. It's O of n time in algorithmic complexity, right? So it's simple enough. I got to move my head again. So this is the code that I came up with. I can move this up a little bit, like that. Slides are tricky. So this is the code I come up with, right? It's just some Python code that does the exact same thing. I start with two lists, L1 and L2, and I have a sorted list. I loop through, and each time I find the smallest one, pop it off and add it onto my result list, and so on and so forth. This is fair enough, not that exciting. I was writing this because I was putting together this example Python code for Earthly, the build tool that I work on. And I just had to do this, but I didn't really want to own this code. It didn't really belong in the example per se, right? It was fun to crank it out, but really I just want a package that I can grab that can merge sorted lists. So I head to YouTube. So I head to Stack Overflow. Basically, I Google how to merge two sorted lists in Python, and I end up on Stack Overflow. And there I find that there's this heapq.merge, which is exactly this algorithm, except it works over any iterator. It takes two lists, and if they're in sorted order, it will produce a new iterator that's also in sorted order. Makes sense, right? But there was a problem. In the answer section, somebody put this, long story short, unless your list is, how many zeros do we have here? Unless your list is 1 million or more, then you should just add these two together and call sort on it. So this person was saying, this, you don't need this fancy algorithm, just resort the list. Which, as I just explained, is not correct, right? It's more operations, it's more expensive to do that. So, basically I have found somebody being wrong on the internet. Time for me to prove them wrong, right? Time to use my algorithmic skills to show them what's what. And so I write up a little bit of comparison, throw it in matplotlib, and I run the results, and I get this. This is sad me, by the way, because what I'm seeing is this heapq.merge is the blue dots, and it is higher in all cases that I measured, higher on the graph is worse. It took more time, where doing this A plus B and resorting is faster. So my intuition and my understanding of how computers work is clearly encountering reality and conflicting. So what do I do with that? That is confusing, right? So I decide to go downstairs, grab some lunch, take a break. Usually a good idea to do when you run up against a problem you don't quite understand. So yeah, I go grab some lunch, I bring it back up to my desk, and I start poking around. Like, how is it possible in Python that resorting a list is faster? And what I find, of course, is TimSort, and this is a commit into CPython. Where's the date? July 31st, 2002. This is just actually the docs for TimSort. So TimSort was created by Tim Peters, whose Git name I guess is Tim-1. And it's complex, so complex that he put in this commit that said checking in the doc file for TimSort because there was too much explanation to put in code comments. He's like, I'm going to throw a whole text file in that walks through exactly what all this is. I mean, for my case, that's great, right? Because, okay, here I could spend my lunch and I can start reading through how TimSort works and how it does this magic trick that makes it faster than merging sorted lists. And so I start reading through his document, which is either timsort.txt or sort.txt. And it starts off, it says, TimSort is an adaptive, stable, natural sort. He named it Tim because he earned it, and he says it has supernatural performance in certain use cases. And look here, he says that sometimes it can have less than log n comparisons. And I keep reading through this document. There's a lot there. It has a section on galloping, which is nothing that I heard of when previously looking into sorts like quicksort or merge sort. I've never heard of galloping. And it has galloping with a broken leg. Then there's merge algorithms, merge high, merge low, galloping complications there below my head. It's a long document in terms of explaining how sort works, right? And it's not even the code, it's just this is what this is doing. But eventually, it starts to make sense. I start to understand this sort algorithm. And it's actually a pretty cool sort algorithm. So in most cases, what TimSort does is based on merge sort. And merge sort is fairly simple. It splits things up, splits them into groups, and then it merges those groups back down together. And as it merges them, it sorts them so that the merged portions all become in order. So it's merging different sorted lists into each other. So that sorting part, merging sorted lists, actually sounds a lot like the problem that I was accomplishing, right? It would be the same algorithm looking at the two lists, putting the smallest one in, and continuing, right? So that is actually part of merge sort, but merge sort has some other steps, which is why I thought I could be faster, right? So in the example that I put together here, right, I give it this list that's like 100, 200, 300, 1, 2, 3, 4, ... And let's say it splits it into these two groups that are now sorted, 100, 200, 300, and then on this side, you have all the rest. And as it goes to merge those, first it compares 1 to 100, 1 is lower, pulls that in, 2 to 100, 2 is lower, pulls that in, and so on and so forth until it slowly pulls all those elements in. Totally makes sense. TimSort uses the same process, but it has, among other things, this step called galloping, right? So you might have noticed when we were doing this comparison, we were always pulling here from the right-hand side, always pulling in these elements because they're always less than 100. And you can see just from the way this list spreads that there's quite a few elements still to pull in before we get to 100. So galloping, the idea that TimSort uses is well, let's speed this up, right? Instead of comparing element by element to get to 100, let's start jumping further out into this one list that we're pulling from and see where we find 100, or basically something greater than 100. And so it does that, right? It starts jumping out. Instead of doing every comparison, it can start moving out sideways. And that's the galloping process. And that means that it can make less comparisons because it can kind of jump through these, doing something like a binary search until it finds 100 in there. And it gets the offset of that, and then it can bring that whole group down. And so the number of comparisons really gets cut down because it doesn't have to go one by one. So that's one of the innovations behind TimSort, and it's actually pretty cool. It's like an insight into how you can move through sorted things faster. So I keep reading, right? Maybe I'm past lunchtime at this point, but I'm pretty interested in learning more about the sort algorithm. So here's the history I came up with. In 1993, there was a paper written on optimistic sorting. It had a couple ideas in it. I believe the galloping idea, and then also the idea that by default, when we measure sort algorithms, we use like random data. Worst case performance is what we're looking at. But the real world isn't actually worst case. A lot of data is partially sorted. And if there's already partially sorted stuff in there, like there might be faster ways to sort than, for instance, than what a quick sort or a merge sort might do. Galloping, is one way to deal with that. The other way that it has is it looks for runs in the data that are already sorted so that it can pick that as a merge chunk. So those are the ideas in the paper. In 2002, Tim Peters, who is pictured here speaking at PyCon, he takes some of these ideas and he implements it in Python. He does a lot of testing and he finds like this is way faster. Part of what his document describes is his method for testing things and showing that this is faster in so many cases. This idea then spreads. So it spreads to Java, it spreads to JavaScript, it spreads to Swift, it spreads to Rust, so much so that right now, whatever language you're in, if you just pick a default sort algorithm, it's likely that you're going to be using some variation of Tim Peters' TimSort. So this is really cool. This is some cool innovation in sorting. But it does leave me confused, right? So all of this explains how you can beat quicksort or merge sort with real world sorted data. But it doesn't really explain why it can beat just merging, just my merge algorithm. Because, I don't have to sort my data. So I need to dig in some more, right? So I start looking into the code. And we can see here is one small part of TimSort on the left, and here's my merge algorithm on the right. One thing that is apparent to me right away is that Tim's algorithm is written in C, and it's running natively when you call sort, where my merge sorted list is interpreted. So maybe that's the reason, right? Maybe I have a whole step that I don't have to do, which is scanning through the list. But maybe TimSort is faster just because it's in C and I have some overhead of being in Python. Right? Interesting idea. So that gives me kind of a light bulb moment, because I've been working on this Python example for Earthly, but I got a little bit distracted looking into merge sort. But if I can rewrite my algorithm in C, then I can put together another cool build example where I'm mixing languages, which is something actually Earthly's quite good at and can be a little bit tricky otherwise, right? Like writing some native C, bringing it into Python, and then using that in Python could be just like a cool use case. And then it means that all my afternoon wasted digging into this stuff was actually for a practical purpose. Also, this would just be cool. Like imagine I can take this algorithm and this advice found in Python that everybody's using and say like, look, I found a faster way and here's my thing, and pull it down from PyPy, and now you can merge things faster. And since there's so much of this going on in the world because everybody uses Python, I'll, save CPU cycles, save forests, save trees, and, they'll have a parade for me. Probably not, but sometimes when I have an idea, I get really excited about it. So this is what I do. I actually get some help from a colleague of mine, and we port my merge algorithm into C. So this is it here. We have, you have to pull in these Python headers, and then, you use pi objects when you want to do a comparison. You can use pi rich compare. It's a little bit more verbose than writing standard Python, but it's somewhat close, right? It's just you have to know what wrappers to use. Like this is pylist get item to get an item out of a list, and then there's also a set to set elements back in the list. But once you do that and you get all the headers in the right place and you compile it, then I can just use it, right? I import my list and I can do a merge just like that. Actually, not that hard. So then I need to whip up a way to build and test this. So on the left, I have my earth file where, I'm installing some dependencies into a container. I'm copying in my C code and my Python code, building it. And then I have some test and some perf steps where I get back out an image. And then on the right is my actual test, right? So I import my new merge package, and I have two different ways to test it. One, using my merge algorithm, one just using the standard sort. And so now I can start testing, like, have I actually made things faster? I'm not trying to beat TimSort at sorting. I'm trying to beat TimSort at merging sorted lists, which should be doable, right? So what happens? It works. The first test I run, I have some Python objects and I try sorting them both my way and the default Python way, and I win. So you can see mine on the bottom here. And this gap represents the savings in CPU time. So that's awesome. This is actually working. I wrote some C code on it and it worked. Kind of strange, but true is what I thought, because this is way outside my expertise area. But then I test it some more. Oh, slides went wild there. But then I test it some more and I lose, sort of. So this is ints. So if I have just a whole bunch of integers in a list and I try to compare my merge against the default sort, I mean, it mainly beats it in most cases, but just by a sliver. And in some weird cases, it's even worse. So once again, my intuition is telling me, like, that doesn't seem right. Why would it matter if it's ints or not? That doesn't make any sense. So I need to look into this. And it turns out that TimSort, besides galloping and looking for runs of sorted orders, it also has some custom comparisons. When we talk about big O notation, when we talk about performance, the N we're talking about is the number of element comparisons, right? But not all element comparisons are the same. Comparing a native C int to a native C int or a Python int to Python int is very fast, but comparing an object to a Python object can be very slow. So Tim's code actually has these code paths where when it's scanning through the list looking for sorts, it also checks the types. And if they're all ints, it says, okay, well, I don't need to do the heavyweight Python object compare. I can just look at the values and see. Or if they're Latin strings, it does a similar thing. And this saves it so much time. So it's actually the same algorithmic complexity, but the cost of each n comparison has changed. And that's how he's able to eke out that speed. So then I just need to repeat that. So I introduce these methods where you can merge by int, merge by float, merge by Latin. I need to have different methods for it because I'm not doing that initial scan through the list. That is actually my performance savings that I don't want to throw away. But I whip these up and then I start testing my code. And now it works. Now I'm getting what I expect. So if I have a list of just ints, TimSort and my generic sort are kind of similar. But if I use my specialized int sort, then I beat it hands down. And I also beat it hands down when it's heterogeneous things. Yes, the world makes sense. Sorting is more expensive than merging, which is awesome, right? So I follow through on my idea. I put together an example for Earthly. I show how you can build in C code, but I also write up a blog post for our blog explaining how this all works and how I made things faster. Because it's just like a little fun adventure, and I wanted to explain it, and I also wanted to brag a little bit. And it does attract some attention online, and so I get some feedback from this guy named Tim Peters, right? He reads my article, and he says, this is great, but what about the galloping? The galloping I described, where you can kind of jump through the list and bring other elements in, that is part of the merge stage, so I can incorporate that code. And then I'd be able to make my merge even faster than linear, because sometimes it wouldn't need to compare every element. It'd be able to jump through. We can beat O of n, which means I have more work to do. If the slides will switch, I will show you what. Okay, so I didn't have time to add that galloping to this merge algorithm, which, with galloping, I think should be called TimMerge. But I'd like to encourage you. Maybe the code is up on GitHub. If you want to work with me on this, we could work on it together. If you're a Python developer and you haven't looked down into the details and played around with C before, I think it's kind of fun. It seems a little bit magical, and like you have superpowers. So you're like, oh, let's get down to the C and let's do something. At least that's how it felt for me. Maybe everybody else is doing this all the time, but I certainly was not. So, it's not as hard as it seems, and I'm looking for volunteers to help push forward with TimMerge. So what did I learn from all this? One of the things I learned is about C code and how you can just get down and write native Python code. It's something that I knew was possible in C Python, but it always seemed just like scary, forbid it. It's like getting down there in the managed memory. And like usually you don't have to. Python is pretty performant if you're doing things in a Pythonic way, but you have a hot loop, you can get in there, you can poke around with things, and it can make a big difference, as I found in this case. So don't be afraid to do that. Another thing I learned is just TimSort is cool. Like, it's neat how these various research ideas about how sorting could work were implemented in Python and made a really solid algorithm. So I think it's just neat to learn about these details. That sort algorithm isn't one that I learned in school, but it's the one that we tend to be using. The other thing that I learned is, intuition is important. I had an intuition about how this was going to work, how merging things would perform, and when that intuition was violated, it either meant my intuition was incorrect or I was doing something wrong. And I think it's important to pay attention to those signals and dig into them a little bit. Otherwise, I would have never stumbled upon this interesting area. And also, I think just like not being afraid to peel back these layers and dive in is something that I'd like to encourage everybody to do, because it can seem like getting out of your depth sometimes to peel back these layers, or at least sometimes that's how I feel it. But it just takes a little effort, and you can learn a lot by just digging in a little deeper. So yeah, I'm Adam. Check out Earthly, and check out me, Adam Gordon Bell. And thank you for watching my talk, my video, I guess, as it were.